An AC electric motor can be considered to be an ideal inductor L in series with the resistance R. The motor is connected in series to a load represented by resistance R load of 120 ohms and a power supply. The power supply has a frequency F equaling 50 Hz and RMS voltage of the supply of 240 volts. When the RMS current through the motor is 0.50 amps, the supply voltage leads the current by 40 degrees. Find the resistance of the motor. Well, there's a lot of information to take in there. As with any electrical question, I think it's a good idea to draw a diagram of the circuit so we can clearly see what's going on. For instance, the resistances, we've got an R load and we've got an R, which appears to be the internal resistance of the inductor, and I could easily get confused and mix those things up. I'm pretty sure that they're different, because otherwise it wouldn't have asked me to find R here in the first place, which would just be 120 ohms, but it's not, because it's different. So let's draw the diagram. So the AC electric motor can be considered to be an ideal inductor. So where's our inductor? There we go, with in series with a resistance R. Okay, so that's our motor. It's connected in series to a load resistance, R load. So series to RL, which we know is 120 ohms. And then there's a power supply as well. So let's just we'll put that in place as well. And because we can write the rest of the information on there. It's easier for me, I don't know about you, but it's easier for me to see it in a diagram. So we've got 50 Hertz and 240 volts RMS. Okay, so now what are we trying to find out again? We're trying to find out R, and we're told that the RMS current through RMS is equal to 0.50 amps. And that the supply voltage leads the current by 40 degrees. So if we were to sketch a quick phasor diagram showing this, we're using the resistances, because remember the RMS current follows the voltage across the resistance, the total resistance of the circuit, that is. So VR, and we've got voltage across the inductor. Remember, the inductor leads because the symbol is L, not because, that's just a way to remember. And then we've got around about, it is not roundabout, it is 40 degrees for the supply voltage, and that's 240 volts. Okay, so straight away, just by sketching out all the information using the relevant diagrams, I think we can see a plan of action. If we know VR, then and we know the current across, VR is the voltage across both those resistances, IRMS is the current through those resistances, so we can work out the total resistance by using Ohm's law in this case, since we're dealing with RMS everything. So R equals V over I. We first have to use our cosine rule to go from the supply voltage to the voltage across the resistance. Once we've got that, then we can calculate our total resistance, and then we have to take away 120 ohms to get just the value of R. Okay, so let's go through that process really quickly just to see how it works out. Okay, let's shift across to the side to do this. So from our phasor diagram, we have, oops, I've got to remember to change back to the pen. We have 240 volts cosine of 40 degrees. That'll give us VR, which equals 367.7 ohms. I haven't calculated it, I'm just reading off the answers to save myself time. So, which is our total resistance. So we have to take away 100 okay, I've skipped just a little bit there. We need R equals V over I, so we have to in between here we have to take that VR, which I don't think it's actually given in the answers, so I'm just going to skip it. But you have to divide it by the 0.5 to get this total resistance here. Once you've got that total resistance, 367.7 minus 120 gives you 247.7 or 250 ohms for that resistance. Okay. Moving on, part 2. What is the total power generated? So total power in the load and in the resistance of the motor. So it's the power, let's do it like that, the power generated in the resistances. Generated, yes, of the motor when the current is 0.5 amps, so same situation as above. So it looks like it's asking 3 things. How much power is supplied to the circuit? Discuss your answers to these questions using physical principles. Okay, so first part wants you to find out the power generated by the resistances. Second part, how much power is actually supplied to the circuit. And then discuss your answers using physical principles. So power from the resistances is actually not too tricky. It's just I RMS, I times V RMS. But it has to be the voltage across the resistance RMS. And we worked that out from the earlier question. Sorry, I've made a brief little mental error. When you're finding the total power on the circuit, it's current times voltage RMS, because when you're dealing with the RMS values, you're dealing with the averages, and that's just the supply voltage and the supply current. So anyway, carrying on. So that is 0.5, we were told was the 0.50 to be significant figures, getting them precise or accurate, and times by VRMS, which is 240 volts. And 120 watts gives you the answer. So that's what the the power across the resistances generated in the resistances. So the heat dissipated in those resistances in the circuit. How much power is supplied to the circuit? Well, that was the supply voltage we used, and that was the total circuit current. Remember, we're dealing with RMS values, so that's a consistent average that you can use. It's representative of the instantaneous average at any point in time. But because it's the supply, that's what is supplied. You can't get any more power in a circuit than what is supplied. So how much is supplied? That much. And why is this? This is what they want to know in the discussion. Why does that happen? Because you've also got the inductor in the circuit. And the inductor, it does stuff. It takes energy to do stuff. Power is the rate of energy consumption. So surely extra energy is needed from the power supply to do that. Well, we've already taken that into account though. So we've taken that into account with using our supply voltage and our supply current, which follows the voltage across the resistance. But these, remember, as we said, are RMS values. So we don't need to worry about what's used and what's not used. However, it's important to note that an inductor only reacts to what's changing in the circuit. So it doesn't actually, it's a means of storing and releasing energy. So whatever it takes in and stores in the magnetic field, well, it's generating the voltage to oppose the change in the circuit. So whatever it takes in that way, it'll also throw back out again with what it's trying to do. So there's no net power change due to the inductor. And that's why we can also stick with this 120 watts. Okay, last question, last part. An energy supply company requires large AC motors to be run with the current and voltage in phase with each other. So current and voltage in phase with each other. Explain how this might be achieved. Well, this is actually very straightforward. Here's your special word. Resonance. We want to make the circuit run in resonance, and to achieve that we have to get the voltage across the inductor the same as voltage across the capacitor. What? There's no capacitor in the circuit? We can explain how this might be achieved. We will put a capacitor in. and this capacitor has to have the same reactance as the inductor. So XC and XL must be equal and opposite. And that will mean that the voltages are equal and opposite, and because they're exactly out of phase, they will cancel out to be zero reactance. So that means you're left with just the resistance, and that means the current and the voltage of the supply and must be in phase with each other. So that's exactly what we're after. Throw in a capacitor that'll match the characteristics, reactance characteristics of the inductor, and you're there.